Thank you, Rob, for the kind introduction and happy 60th. Bob said, really young, and I think de-emphasized the really, and I don't know about the young. And so all that's fine. So just a disclaimer, if you've read the abstract and if you're here to hear about the Allen Institute and brains and so on, it's not the right place, or maybe I'm not in the right place. The other thing is the gentleman who gave me this laptop to use is not here. So I'm not sure how to get to the talk. Entropy? Why not? Not really. So I'm not really sure what to do at this point. Okay, it's certainly a pleasure to be here. So today I want to talk about non-smooth optimization. This is work that kind of has grown out of this whole area of compressed sensing that's mushroomed, I'd say, the last 10, 12 years. And so I want to give a little bit of history with regards to the area. Okay, so as I said, I'll be giving a little bit of a history of what's been going on, mostly from a personal, I would say, point of view. I'll try to refer to other work. You can't hear me. Okay, then I think this is how I'm going to be the whole talk. Okay. So this is joint work with one of my graduate students, Chris Thrambulaitis, and a former student, Samit Oymak, who's now a Simons Fellow at Berkeley for the information theory, I guess, semester that's going on over there. Now, I have a third student who's not a co-author on this, Matt Thill, and he kind of has this rule that he's told me, and he says whenever you put someone's name in your talk, you should make a bar joke about the person. And so I was here about a year ago at UCSD, and there were 3 other names, and I made a bar joke, and so Alon kind of, when I sent him the title, said I should do this. And so here is my attempt at a bar joke. So this is a lame bar joke. It's more a tribute to Dave Slepian. We'll see his work, how it relates to the current talk. So Dave Slepian, as you know, was one of the most distinguished information theorists of the past century. By and large, I think he was at Bell Labs for his entire career. And so let's assume Dave Slepian goes to a bar, okay? And so he meets the waitress, and the image looks back, but there's a nice waitress over there. And so the question is, what does the waitress say? And so A, does she say, Claude just came in? So Claude is clearly Shannon. Now, why am I saying that? Well, Slepian was the first person to win the Shannon Award in 1974, but he was not the first Shannon lecturer. The first Shannon lecturer was Shannon himself. And so that's why Claude came in before Dave. Or B, this is UCSD, and so maybe appropriate. Does the waitress say, will you be waiting for Jack? Does anyone know who Jack is? Jack Wolf, right. Slepian Wolf. So that's a reasonable thing. Maybe he'd be waiting for Jack. This one is a little corny, but bear with me. And so does she say, will you be attending the function? And so Dave says, what function? And so what function is it? Here you go. Sergio knows all of these things. So it's a prolate spheroidal wave function, to which I guess Slepian says, no, I'm with a different group. And again, this refers to the work he did on group codes. Now, the problem I'm having is I have a D and an E, and I don't see them. No, okay. So the D's now, this will be a problem throughout. This is for working now. So I have to tell you what D is. Higher? Can you hear me now? Okay. So this will be a problem throughout then, if I'm not getting the bottom of this. So D basically is, she asks, will you be joining the French table? Now that's a real inside joke, and so if you don't know what that means, maybe ask the old-time Bell Labsers about the French table. And E basically is none of the above. And I'll come back to this, and we'll see what the correct answer is. So there were E answers, and I apologize that they're not here. Okay, but as for the outline of the talk, let's get a bit more serious. So I'll give a brief introduction to the problem of structured signal recovery, how it relates to non-smooth convex optimization, and I'll focus on a particular algorithm called lasso and a generalization of it. Then I'll make connections to Slepian and Gordon, two lemmas that we'll use to analyze these, and then I'll use this essentially to analyze the squared error of the generalized lasso algorithm. And as a result, we'll see things like Gaussian widths and statistical dimensions, and we'll learn how to optimally tune parameters that occur in these optimizations. Depending on time, I'll say a few words about generalizations, and then I'll conclude. Okay? So as a brief introduction, I mean, everyone knows this. Big data is a buzzword these days, and so we're increasingly confronted with very large data sets where we need to extract some signal of interest, right? There's a deluge of data. And this comes up in machine learning, in image processing, in all kinds of applications involving sensors, in wireless comms, signal processing, statistics. Those are the areas. These are some of the applications. I've mentioned a few. Social networks is another. DNA microarrays, sequencing, so on and so forth. And so on the face of it, you know, one might worry about the curse of dimensionality with all of these things. And so fortunately, it so happens in many applications, even though the data, you know, the ambient dimension of the data could be very large, the signal of interest lives in a manifold, if you will, of much lower dimension than that of the original ambient space, and so one would want to leverage that. And so this is what's called either compressed sensing or compressed recovery, and the idea is to have signal recovery methods that are computationally efficient and do not need to access the entire data. Okay? And non-smooth convex optimization is one way to do this. And so basically, the idea is as follows. You have an observation vector, say m-dimensional, y, and you want to obtain information about some structured signal that's not directly observable x, say n-dimensional. And to do this, you have a convex loss function of both x and y, of the observations and of the signal you're interested in. Could be a log likelihood function, for example, that you would like to minimize. But you also have a non-smooth prior or regularizer that induces structure called f, and this is often convex, but it's not smooth. And so the generic problem you're interested in solving is either, you know, a weighted combination of the loss function and the regularizer, or you minimize the regularizer subject to a bound on the loss function, or vice versa. Either of these three. And as you can imagine, they're all related, and, you know, the machinery I will describe allows one to analyze all of these, but I'll really focus on the first. Okay, so this was the setting. Now, there's a lot of interest, as I said, in this problem, and I would say there's basically two ways or two places where there are challenges. One are algorithmic issues, right? So often, you know, there are many thousands or even millions of variables here, and so it's really important to have algorithms that are scalable. You often want to do these things distributedly. Maybe the data sets are all over the place. Maybe you want to send things to the cloud to do it, and so on. So there's a lot of algorithmic issues. I won't be talking about any of that today. What I will be talking about are questions related to analysis, okay? And so the questions you might be interested in is, even if I go ahead and I do something like this, can I recover the true signal? And if so, when, okay? So in these types of problems, you know, there are many problems where you do optimization. Maybe you're minimizing the energy consumption in some network or whatever, where the goal is actually what you're trying to optimize. In these problems, you know, the optimization problem is really a means to get to the end, which is recovering the signal, right? And so the question really is this the right means? And so that's what this question is trying to address. And if not, if you can't recover the signal perfectly, what is the quality of the recovered signal? For example, what's the mean squared error? And then how does the convex approach compare to one with no, maybe I should do it this way so we can see the ball. There was none here. How does it compare to approaches where there are no computational constraints, right? So if you don't go through, say, these types of optimizations. The flip side is then this doesn't go with this pointer. Where is the full screen? Ah. I'm tempted to do something. I did have the D&E. So that was there. Okay. Okay. Anyway, we'll come back to that slide. Okay, and then finally, the question is, how do you choose this regularizer, or how do you choose these constraints C1 and C2? That's important. Okay, and so here's an example that we'll visit quite a bit in this talk, which is the question of noisy compressed sensing. So you have your signal X. It's k sparse, meaning that only k of the n entries are non-zero. Often k is much less than n. And we make m noisy measurements of this signal. So you have a measurement matrix A. And so this is what you have. It's an m by n matrix. And you might ask, how many measurements do you need to find a good estimate of x? And if you have no computational constraints, solving this problem in principle is doable. You could, for example, search over all k columns of A, and for each one of them attempt to solve this least squares problem, right? And so that way you would find the best k-sparse solution, certainly. The problem is, of course, this is an exhaustive search. You have to do n choose k such least squares problems, and nobody can do that. And so this is ITA. I don't know whether I should put that up here. But so the question of, if you have no computational constraints, what happens is maybe not as interesting as the computational problem, which is, can we do this more efficiently and for what values of n? Okay? And of course, there are other problems. I talked about, the sparse signal recovery, but you could think of recovering low-rank matrices where you can't even enumerate all possibilities. So you can't enumerate all low-rank matrices, and so even exhaustive search is not possible to do. Okay? And so here is the lasso algorithm we'll spend some time on. It's a way to try to solve least squares problems when you have a sparsity constraint. It goes back to Tibshirani in ~96. So essentially you minimize your quadratic term, and then you have a regularizer, which is an L1 regularizer, which I'm sure everyone knows, kind of enforces sparsity. And lambda is the regularizer parameter. And so the questions you're interested in is how to choose lambda. What is the performance of the algorithm? So if I solve this, what can I say about the quality of x hat? For example, what is the mean square error? And so these are questions that we will answer by the end of this talk. Okay? One can think of a generalization of Lasso where, it's again the same thing. So you have the quadratic term, which is trying to make your measurements, match the signal, and assuming, you have Gaussian noise or some noise with bounded variance. But you might have other priors. And so you could think of having another convex regularizer which induces different types of structures. So as I said, the L1 encourages sparsity. I apologize if I'm going slow. People know this. The nuclear norm of a matrix, which is the sum of the singular values, encourages low rankness. So if you have a matrix, say X, this would be the problem. Then there's many other things. Here's another one. This is the mixed L1, L2, which encourages block sparsity. So essentially, the cost function is you add the two norms of the different blocks where you think the signal might be block sparse, and so on. Okay? And so generally, this is what the problem looks like. There's a loss function, as I said, and there's a regularizer. If the noise is Gaussian, it makes sense to put a two norm here, and that's what the lasso and generalized lasso do. But if you have, for example, sparse noise, you might put an L1 norm here. So if the noise is only perturbing a subset of the entries of Y. If you have a noise that's bounded in amplitude, then you want to put an infinity norm here. And again, and so on. And in fact, in machine learning, people have things like support vector machines and binary logistic functions and so on. And those can more or less be put into this framework as well. Okay? But I want to focus for the time being on this problem here, generalized lasso. It's been extensively studied until, I would say, the last 2-3 years, and I'll give a bit of the history of this. Most performance bounds were quite loose. And so the question is, if we look at the performance as the mean square error, can we compute it? And can we determine the optimal regularizer? It turns out we can. Okay, and just to give you a teaser, here is an example. So here is the situation where you have an n by n matrix, n is 45. It has low rank R, in these simulations R is 6. We make Gaussian measurements of this. So there's some matrix A, which is a Gaussian matrix, so it kind of mixes up the entries of of x, and then you add noise to it. And this is the problem you're trying to solve. And so in this particular case, the number of measurements is some number, 0.6 times n squared, so it's compressed. You're not seeing the entire matrix. And so what I'm showing is actually the mean square error as a function of the parameter lambda. And the blue is the theoretical curve, and the red is kind of a Monte Carlo simulation. As you see, it agrees perfectly, and it also allows you to see that there is an optimal lambda to choose, which has the best performance. And we'll come back to this and interpret what this means and all of that. Okay, now, as I had said here, before I get into this, it's, I think, appropriate that I tell a little bit of an earlier story. And the earlier story is the Noiseless case, which has been studied more, but will kind of give us some of the elements of what we'll need for the noisy case. So in the Noiseless case, again, we have our desired signal. It's k-sparse. K is a lot less than n. We have this m by n measurement matrix. The only difference is there's no z here. So there's no noise. And a heuristic that's been around for many, many years is the L1. I'm sure you're all familiar. You minimize the L1 norm of x subject to y equal to ax. Essentially because typically you'll take fewer measurements in the ambient dimension because k is less than n. And so there are many solutions to this equation, and you choose the one that has the least L1 norm, the hope being that you'll find the k-sparse solution, right? So the algorithm was around for a long time. This whole area got jump-started with the papers of Candace, Tao, and Donahoe, seminal papers I'm sure you're all aware of. And what they showed was that under certain conditions called restricted RIP, the restricted isometry property, then under those conditions, actually this thing works. So people had thought that this was a heuristic, whereas these fellows actually gave conditions on the matrix A, so this always works. So you can recover the solution without an exponential search. Okay, and so this is what I was saying. These are the RIP conditions. The original analysis of Candace and Tao gave order optimal but very loose bounds. So they were orders of magnitude off the performance that one saw in practice. Okay? And so what I want to describe is a more general framework to kind of set things up. And so let's suppose we have a structured signal x naught. And there's a structured inducing norm associated with it, which I'll call f sometimes just by this norm. And we have access to linear measurements of x naught. Okay, so A is some linear operator, and what we're going to solve is to minimize this structure inducing norm subject to the observations. So Ax naught is what we observe, but we don't know what x naught is. We want to find it essentially. Okay, and so I've talked about different examples of this. Now, an important set when you're trying to figure out whether this works or not is this set U, which is the set of vectors z. So suppose x naught is the optimal solution, or the true solution that I'm trying to recover. Okay, so the set z is the set of vectors such that when I sit at x naught and I perturb the solution by z, the solution goes down. So these are kind of, if you will, the descent vectors when you sit at x naught. These are the directions, if you will, that if you go down on, you can improve the solution. You can reduce the norm. And so if you think about this, it's kind of easy to see that you will get the solution to the problem is the unique solution to the convex problem if and only if this holds. So the null space of A has no intersection with this set. And why is that? Well, if you look at sitting at x naught and kind of perturbing by a z, the only z's that are consistent with your observations are z's that live in the null space of A. Okay, so those are the only z's I'm allowed to perturb x naught by. Okay? And if it so happens that none of those guys is in this descent set, then we're done. X naught will have to be the optimal solution. Okay, so this is an important slide to kind of think of, right? Because in order to guarantee the constraint, the only z's I can add, so x will have to be x naught plus something in the null space for this to hold. And if nothing in the null space intersects with this set, there is no direction in the null space that takes the cost down, and so I have to be optimal at x naught. Okay? So that's what that means. Okay? And since the null space is a linear subspace, I can replace this set with its cone. Whether you intersect a set or not is the same as to whether you intersect the cone. Okay? So that's what this is. Okay, and so it turns out one can characterize this cone, and I will in a second, in terms of the subgradient of our convex function at the optimal point x naught. Okay, so let me remind you what the subgradient is. So we have some non-smooth function like this. if I look at the subgradient at any smooth point, it's just the usual gradient. If it's at some point that's not smooth, say is this x naught, it's basically the set of vectors such that if I pass a line with that vector as the slope through x naught, it lies beneath the curve. Okay, and so that mathematically that's what this is saying. So this is a line with slope v through x naught. If it's always less than x for every x, this vector v is in the subgradient set. Okay? And since this is a convex function, the subgradient set is a convex set, for those of you who know. Okay? Now why is this important? Maybe I'll skip the details here, but you can kind of see because this is kind of something in your null space if you think about it. So it turns out the cone of this undesirable set is just the set of vectors z that have an inner product that's negative with every vector in this subgradient set. Okay? Because in some sense we want to make this quantity here negative. Again, I can make this more rigorous, but this is the cone. So the cone is essentially vectors z that have a negative inner product with everything in the subgradient set at x naught. And again, this is a special cone. It's called the polar cone of this set. Okay? So let's assume this is a set, C. So the set of vectors whose inner products are negative with this are the set of vectors that make an angle bigger than 90 degrees with this, right? Because the cosine of anything bigger than 90 is negative. Okay? So if this is my cone, if this is my subgradient set, this is the polar set. They put a superscript O for the polar set. Don't ask me why. And so the condition basically boils down to the null space of the measurement matrix should not intersect with the polar cone of the subgradient evaluated at the optimal point. Okay, so this captures everything, and it captures everything in a very nice way. The measurement matrix shows up through the null space, the function shows up through the subgradient set, and the optimal point shows up through the point at which we're actually looking at the subgradient. Okay? So this is if and only if. Okay? So if you want to know when the methods work, that's the condition. Okay, and so that's just repeating what I said. Now it turns out that, while in principle it's kind of easy to, in most cases, figure out what this polar cone is, checking whether a particular null space of a matrix intersects with it is difficult. And so what people do rather than focus on a particular A, they look at a family of random A's and ask the question, well, I can't determine whether this holds for a specific A, but maybe for a family of random A's, I can determine whether this happens with high probability or not. And so that's what people have been doing. And so the customary assumption is to assume that this measurement matrix A has IID zero mean unit variance entries. I'll talk more about this later. And in particular, if things are Gaussian, I should have said that. The good thing about this is it makes the null space of A rotationally invariant. So if your A matrix has IID Gaussians in it, the null space has no preference being in any direction. It's equally likely to be in any direction. And so essentially what the condition is saying is you have your cone of the subgradient at x naught, you generate a null space kind of in a rotational invariant way, and you wonder what the probability is that you intersect with that particular set. Okay? So this is something that people can compute. And this is called the Grassmann angle of the cone. It's a generalization of the usual angle. In 2 dimensions, if you have an angle, if you kind of think of the angle being inside a circle with the, I guess, apex being at the center of the circle, if you randomly generate a line through the center of the circle, the probability that you intersect this angle is just the angle over 2 pi. Right? So that probability is related to the angle. And so this is a generalization of that notion. You have a cone, you generate a random subspace, the probability of intersection is called the Grassmann angle. It's a little more complicated than the planar case because what also matters is the dimension of the subspace that you choose. So the Grassmann angle not only depends on the cone, it depends on the subspace that you're generating. Okay, so that's kind of where things are at. And so it turns out that Dono and Tanner in 2005 made note of this, and they actually, for the L1 case, computed the Grassmann angle. And so they essentially found out what the recovery thresholds were. The calculations are very cumbersome. There's exponentially many inner and outer angles that you have to compute because the cone is polyhedral. Very complicated stuff. So I had a very persistent student, Wei Yu Xu, in 2007, who actually generalized this stuff and did even more cumbersome calculations. But it's very difficult, okay? And so with Ben Recht, we tried to do this for nuclear norm, and we weren't really able to, because the nuclear norm cone is not polyhedral. It has curvature. And so we really didn't know how to compute these Grassmann angles, and we only had bounds, even though we worked really hard. And so there was another framework kind of in the work of Rudelson and Vershinin in 2006, where they suggested this. We were not aware. And then one of my former students, Mihailo Stojnik, really used it in 2009. It uses something called escape through mesh and Gaussian widths. I'll talk about this a little bit later. And so using this new framework, he could rederive the result for sparse vectors, and he could get new results for block sparse vectors, which we were not able to do earlier. And it's much simpler. Emphasis on much, as many as you want. I mean, there's no comparison in terms of what it takes to compute using this framework and the one up there. Okay, and so the approach was such that, so for example, there's an important paper by Chandrasekhar and Perillo-Wilski that used this idea. They introduced this idea of atomic norms and used the Gaussian width as a way to analyze the performance. We were finally able to settle the question for nuclear norms because Stojnik's approach allowed that. That's work with Summit. Michael McCoy and Joel Tropp have used this to study deconvolution. So if you have two sparse signals that are kind of mixed, and you want to separate the two. And so the Gaussian width stuff was abound. In 2013, I guess Stojnik showed that it was tight. And there's actually a paper, again, by Amelunxen, Lotz, McCoy, and Tropp that in the general case show these things are tight. So that's that. And I should also mention that there is a parallel body of work that use ideas based on the replica method, which obtain a lot of the results that I mentioned. The caveat being that replica method is not really rigorous. But again, this may not be the extensive list, but I believe these are papers that use replica method to answer a lot of these questions. So Shlomo and Vivek and people from our community are clearly here. Okay, what about the noisy case? So to the best of my knowledge, the noisy case was first studied by Baiati, Montanari, and Donahoe in 2012, where they gave formulas. And this, I think, in fact, in 2012, Donahoe gave a plenary here, mostly talking about this stuff. It's a little different because it uses something called approximate message passing, which I confess I don't fully understand. But it's a very nice piece of work. In 2013, Stojnik developed yet another new approach. And our approach is inspired by that. And it turns out that using this approach, it subsumes everything that was done earlier, the noiseless and noisy results. It allows for much more. And it's the most natural way to study the problem, in my view. So if you want to write a textbook, I think, on this stuff, I think this is the way to present it. And so the question is, where does this all come from? And now we go back to Dave Slepian. So recall he went to the bar, and Shannon came in, and he was waiting for Jack, and so the correct answer is none of the above. Even though, all of these are reasonable things for the waitress to ask Dave Slepian if he went to the bar, for the purposes of this talk, what she would have asked is, would you care to compare our beers? And that's because I want to talk about his comparison lemma, which is yet another of the stuff that he's done. And so this is a paper in 1962. It looks very inconspicuous, and so I'll go through it, but it's extremely powerful. So let xi and yi be two Gaussian processes. Okay, so they're indexed by I. They're Gaussian. They have the same mean mu I. So each xi and each yi have the same mean, and they have the same variance. Okay? And furthermore, if I look at the correlation, if you will, or covariance or whatever, x has higher correlation, if you will, than y. Okay, so that's what this means. So I'm looking at, x minus the mean multiplied by x minus the mean. In one case, the subscripts are I, and the other one is I prime. So I'm looking at two instances in the process and how correlated these are. And I will assume that for every I and I prime, the x process is more correlated than the y process. Then, so Slepian is able to compare essentially these two probabilities. So in one case, you look at the probability that the maximum of the process I is bigger than some value C. In the other one, it's the maximum of the Y process being bigger than C. And so which direction do you think this inequality goes? I'm sure you guys know, right? I mean, it should go, you know, I mean, the mouth should open, if you will, to the right, right? Because Y has less correlation, so more variation, exactly. And so it has a better chance, of you know, exceeding a value C than this one does. So this seems very intuitive. In fact, the proof is not too difficult. You know, you can probably give it to a good student and they can do it. But it's not trivial either, but a good student can do it. No, I don't know if I could, but anyway. The other thing that's interesting is this is generally not true for non-Gaussian processes. Okay, so the Gaussianity is critical. That's why the proof is not trivial, because you have to exploit the Gaussianness. It's not just something based on second-order statistics. There are, for example, simple binary processes which violate this. So what is this good for? Right? This looked very, as I said, inconspicuous, very kind of obvious. Well, Slepian was interested in bounding the maximum, or studying the maximum singular value of a random matrix with IID entries, say m by n. And so sigma max you can write in this form, the max over u with 2 norm 1 and v with 2 norm 1 of this, if you will, bilinear form. Okay? And so this is how he did it. He defined two Gaussian processes. So these Gaussian processes are indexed by u and v. Okay? So this is one. That's where it came from. And I added gamma to it, which is just some Gaussian n01 independent of everything. But then I create also this y process, uv, in this particular way. So it's the inner product of the vector u with a Gaussian vector of dimension m, and the vector v with a Gaussian vector of dimension n. Okay, so these are inner products. So this thing here, they're both Gaussian processes, because this is just the sum of Gaussians, this is just the sum of Gaussians, right? And everything in sight is IID. Here it depends on a Gaussian matrix. These things depend on Gaussian vectors, okay? And it's not too hard to see that these guys are zero mean, because everything was zero mean. And the variance, in fact, is 2, if you calculate it. On this set where u is 1 and v is 1, the variance of both these guys are 2. This is variance 1, that's variance 1, and likewise here. Okay? So it satisfies the first assumption of Slepian. They have the same mean and variance. And then if you actually look at the correlation and you calculate it, it's not too hard to do. You know, and it turns out that, for example, the x guy what ends up happening is you get the inner products of the u's multiplied by the inner products of the v's. So I'm taking two different points in the process. One is indexed by uv, the other one by u prime v prime. Okay? So that's what this is. That just has variance 1, and then I'm subtracting it, the covariance of this, and it turns out that's what this is. And when you stare at this, you realize, aha, I can factor this, and this is actually non-negative. Okay? So that's interesting, right? So this process here is more correlated than this one, and so we can use Slepian's result, right? So therefore, the probability that this maximum exceeds C, because it's more correlated, is less than this other guy, which is less correlated. Okay? Is this clear? This is just directly Slepian's lemma. Okay? Now, if you look at these things, so what Slepian is interested in is this quantity. This gamma is a nuisance. But we can get rid of it because it's either positive or negative. Half the time it's positive, which is bad. And so that you throw away and you get a 1/2 probability here. And then if you look at this thing over here, this maximization is easy to do because u and v are unit norm. They'll just align themselves with g and h. And so that's just the probability that the norm of g plus the norm of h exceeds c. Okay, so why is this useful? This lemma is useful because if I have a good upper bound on this quantity, so if this probability is small, so if C is a good upper bound, this probability will be small. C will be a good upper bound on the norm of A as well, because this probability will be small, and by fiat, this has to be small as well. Okay? And so if you look at this quantity here, G and H, basically they concentrate around, root m and root n, because they're m-dimensional and n-dimensional vectors. And so this means that the probability that A significantly exceeds this is very small. Okay, so we found a probabilistic bound on sigma max, or on the norm of A, as root m plus root n. And we did this by analyzing this much easier optimization problem. Okay, so that's the idea. Now, what's the next thing you would do? You'd say, well, okay, we did sigma max. Wonderful. Let's do sigma min. But then, whoops, we have a min up front here, right? This is sigma min. And that's the problem. We can't use Slepian's lemma. Does not apply. And it took 24 years. Again, people analyze sigma min through other methods, but using this method, it took 24 years before people could use something like Slepian. And that takes me to Gordon. Okay? And so here is Gordon's comparison lemma in 1988. So again, I have two Gaussian processes. Now I'm indexing them by an I and a J. Okay? So Xij and Yij are two Gaussian processes. They have the same mean and the same variance. Okay? But now when I look at their correlation, things are a little more funky. Right? So if I first correlate things by fixing I, the first index, and then playing around with the second index, J and J prime, the X's are more correlated than the Y's. But if I let both of them to flip, then suddenly, I think I misspoke. The Y's were more correlated here, now the X's are more correlated here. So this looks bizarre. But it turns out that when this is true, then you can actually compare these two events. So this is the process Y, the probability that the min over the index I, the max over the index J is less than C, and here the same thing for X. And what way do you think the inequality goes here? Now this is tricky, right? It goes the same direction. Again, if you think about it, if you get rid of the I, then it boils down to the previous case, and you could have guessed. But it looks bizarre. And in fact, Gordon has a generalization of this, which is for the mathematical masochist in you, where you have multiple indices on the X's and Y's, and you keep on flipping the indices I, J, K, L to I prime, J prime, K prime, L prime, and these expectations keep on flipping, and you have a sequence of min, max, min, max, min, max. Fortunately, we don't need anything more than this for this talk, okay? So using this, Gordon actually can prove the following lemma. And so this is important. So let G be an m by n Gaussian matrix, gamma a Gaussian random variable, G and H random vectors. They're all IID 0, 1. Let Sx and Sy be some compact sets, and let phi be some continuous function of the arguments x and y. And so let's look at two optimization problems. In this first one, I'm calling it with capital phi. It's a function of the capital G and the gamma. I minimize over x in its set, and I maximize over y in its set, this thing. So there's that term, there's a term like this and this. And then I look at another optimization problem, little phi, which is a function of vectors G and H, which is the same minimization and maximization, except the function is easier, right? So I take the norm of x with an inner product against the Gaussian vector and the norm of y with an inner product against another Gaussian, and I put the same sign. Now, using his lemma, I will spare you the details. Gordon shows that you can show the following thing. So the probability that this little phi, this is an easier optimization, is less than c, upper bounds the probability that the big phi is less than c. Okay? So what that means is that, for example, if I have a high probability lower bound on phi, so if I have a c for which the probability of being below it is low, this c is also a high probability lower bound on the capital phi. So by solving this optimization problem, if I can analyze this, it says something about this one, which ostensibly looks more complicated. It is, in fact, more complicated. And so this is the basis for things like escape through mesh and Gaussian width, which I won't talk about right now. You can actually use this, and this is the main application, or the first application that Gordon had to show that sigma min behaves the way you think it should, which is this. But I won't do that now. Okay? What I want to show you now is a stronger version of Gordon's lemma. So this is the work we did with Samet and Christos. And so let me walk you through it. So now it's a little different, and you'll see. So I have an optimization problem, capital phi. It's just a function of g. So there is no this nasty term is no longer there, because that's a nasty term. I don't like it. So it's this bilinear form in G plus some function psi, and I have this simpler one phi of little g and h, which is just this thing. It's exactly what it was earlier. And so here is the statement. Okay, so the first one is that, again, if you have the probability that phi being less than c, little phi, upper bounds, maybe half the probability that capital phi is less than c, okay? So you have to put in a factor of 2 because I dropped one term there. But again, it doesn't matter. If what I'm looking for is a good lower bound on phi, I can get it by constructing a good lower bound on little phi. Okay? Now, this is an interesting result, and it's very general because I haven't said anything about what this function is or anything about what these sets are. But often we care about convex sets, and we care about functions that are convex concave. So in fact, if these two sets are convex, and at least one of which is compact, and if this function here is convex in x, which is what I want to minimize over, and concave in y, which is what I want to maximize over, so this is a nice setting for a convex optimization problem, then you can say much more. It turns out that, and it's as you would expect, it's through a duality argument, that if this little phi concentrates to some value c, then the same is true for capital phi. So if the probability that this little phi doesn't deviate from c, if this probability of deviating from c is small, the probability that the capital phi deviates from c is small. Okay? Now I should say, so there's a third statement in the lemma which I'll show you in a minute, but again, I do want to make a disclaimer. The innovation in this theorem is really the statement of the theorem. It's not the proof. The proof is trivial. It uses convexity. And so there's sometimes, I think, results in math where the statement is obvious, the proof is hard. There's sometimes where, once you have the statement, the proof is obvious, and this is one of those cases. And so the third one has an additional assumption. So if you look at this maximization, the minimization over x, right? So if you look at inside, I have a maximization over a linear function in x and a convex function in x. And so the maximum of a convex function is convex. So this is why minimizing over x is convex. So if in addition I insist that the optimization over x is strongly convex, not just convex, but strongly convex, meaning if I'm sitting at the optimal and I perturb, then I don't move a lot. And if this phi happens to concentrate, then here is the statement. For any norm, and mind you, any norm, for which the solution to the second problem concentrates, so that x hat is the norm of the solution to the second problem, with high probability, the solution of the upper problem will concentrate to the same value. Okay, so this is saying a lot more. The first two statements were saying something about the objectives. This is saying something about the solution. Okay? Now, again, the reason why this is so surprising is, there is no organic connection between these two problems. This depends on a G, capital G. This depends on some other random G and H. There's no reason why the solutions should be the same, and they're not, because the problems are generated differently. But if the norm of one solution concentrates, the norm of the other will concentrate to the same thing. Okay? And that's what we'll use. And so let me give you a couple of examples of this. So let's look at least squares, just standard least squares. How much time do I have?
It's about 15 minutes.
15 minutes? Okay, I can say something. So let me look at least squares to show you how this is useful. Okay? So standard least squares, let's forget about convexity for the time being. I have an unknown vector. I'm hitting it with a measurement matrix. And I'm adding noise. I'll assume the measurement matrix and the noise have IID normal 0, 1 entries. Well, I guess A does. The noise, let's say, has normal sigma squared entries. Okay? And x naught is the unknown signal. And this is standard least squares, so I need at least as many equations as unknowns, and so let me assume that. And so least squares says choose x to minimize this. Right? Very simple. We know the solution is the pseudo-inverse. We know all kinds of things about this. But let's see what Gordon's lemma tells us about this. Okay? So to do this, I'm going to write things in terms of the error rather than x. And so I'll call w the error vector. It's the difference between the true x and some value of x. And so that allows you to write y minus ax in this form in terms of the noise, replacing y with ax plus noise. And so the minimization over x, you can write like this. Again, this is not a meaningful problem. You never minimize over W because you don't see Z, but they have the same values. The objectives are the same. Okay, and so the 2 norm, we all know we can write as a maximization over the dual norm, a bilinear form of the dual norm. And so now that's what this is. We're getting towards Gordon's lemma because we have a min and a max. And then if we rewrite A and Z as IID Gaussians with 0 mean and unit variance, this is what happens. And this is now ripe for Gordon's lemma, or our strengthening of it, because this is a bilinear form in an IID Gaussian. This is minimization and maximization over a convex set, and one of them is compact. So everything holds. And so the simpler optimization is this. Okay? So if you recall, what you do is you get rid of this Gaussian matrix. You take the norm of this vector, which is this, multiply it with u times the Gaussian vector. Then you take the norm of this vector, which is u, multiplying this vector here with the Gaussian vector. Okay, so that's all it is. And G is in Rm. These guys are have the appropriate dimensions. So I need to do this. And if you look at this, maximization over U is easy because I just have to align myself with G. And so that's this. You're left with a minimization over W. You look at this. This is also easy. At least if I fix the norm of W, because this only depends on the norm of W. If I fix the norm, I also know how to minimize. I just align with the negative of H. And so I get this. And so that's what it is. And so alpha is the norm of W. I only need to solve this. This is easy. You can solve by differentiation. Anyone can do that, even me. And this is what you get. You get this. And then when the dimensions grow, this goes to n, that goes to m, and so you get this quantity here. So let me summarize. So alpha, if you recall, was the norm of the solution in the easier problem. But by our lemma, it's the norm of the solution in the harder problem. So this is what we've shown. That the squared error over sigma squared is this. It's the ambient dimension n over the number of measurements minus the ambient dimension. Now, of course, in least squares, as I said, we know what the solution is. We know what the squared error is. This is a Wishart matrix. We know what the eigenvalues are. And if you do that, you'll get the same results. It's not clear here whether you need all this machinery. I was just showing you how it can work. But when you looked at generalized lasso where we don't know what the solution is, you need this machinery. Okay? And so this is exactly like least squares, except I have this regularizer, right? And so again, I can do the same trick that I did with this. And if you do that, you get this simpler optimization. If you recall, this first part is what we had for the least squares. The only thing that I've added is a regularizer. And I've written things in terms of W rather than X. So X is X naught minus W. Okay? And in fact, the maximization over U again is easy. I just align myself with G. Okay? So I'm here. I need to study this. And I can do this in the general case, but it's easier if I assume the variance of the noise is small, and you'll see why. And so I'll focus on that case. When that is the case, this convex thing here, you can kind of lower bound it by the value at x naught plus the sup over the subgradient set of a vector in the subgradient times minus W. Okay, so this is kind of like the lower bound we had in subgradients, and I'm choosing the best lower bound, hence the sup. And when sigma is small, this is very tight, and you can make it rigorous. In the interest of time, I will not. And so when sigma is small, we get this problem. I just replaced that with this. I threw away this first term because it has no effect on the minimization. And then if you reorganize things, so this W I can factor out. So I'm doing two things here. First of all, I took this lambda, I put it on the S. That's scaling S, and so therefore I'm scaling the subdifferential. And then I just combine the two terms that have W in them, and so this is what I get. So this is this term plus the sup over S's in the subdifferential of this thing. Now again, I need to minimize this over W. Fixing the norm of W, this is easy to do. Again, what W will do, because it wants to minimize, it will align itself with the negative of this vector. And the norm is alpha, so that's what you get. Alpha goes over there. Now the sup of something negative is the inf, is minus the inf of that thing. And so you get this. And so this is precisely what we had earlier. Earlier we had square root of alpha squared plus sigma squared norm of G minus alpha norm of H. Now it's this thing. So let's see what this means, right? So H here is a random Gaussian vector. S is a vector in the scaled subdifferential. Okay, and this is the distance between the two. And I'm searching over all S at the one that minimizes this distance. So in some sense, this is the distance between this Gaussian vector H and the set itself. Because I'm in 5 minutes. Because I'm minimizing over all elements in this set. Okay? So that's what the geometrical object is. You have this scaled subdifferential, and we're looking at the distance to that. And again, if you take derivatives, this is the formula that you get. What I've written here. Okay? So it's precisely what we had earlier. This used to be n, now it's this thing. So the ambient dimension is replaced by this object. And so here's a picture. So this is, say, the subdifferential. It's a convex set. This is the scaled version. I'm generating a random h, and I'm finding the distance to that. Okay, that's what, or the squared distance, if you will. I'll call the squared distance because what showed up here was the squared distance. D. The expected value of that I'll call d of the function f at point x naught with scaling lambda. And it turns out that this thing, when you generate, so this is random because it depends on generating this random h, but it turns out it concentrates to this value. Okay, so this quantity, the squared error over sigma squared, goes to this. Okay, so that's the main result, right? The ambient dimension is replaced by the distance to the scaled subdifferential at the optimal point. Okay, so that's what I've said. If you want the best lambda, then you have to, essentially, if you look at this function, this is a decreasing function in d. And so if you want to minimize this, you want to minimize d. So you want to find the lambda such that the distance, the squared distance, is as small as possible. And if you think about that, that's just the distance to the cone, right? Because if you look at this picture, if I want to choose a lambda to minimize the distance, so as I scale lambda, I generate the cone. And so the best lambda will be the projection onto the cone itself. That's how you find the best lambda, lambda star. This quantity I'll call omega squared. And in the literature, this is called the squared Gaussian width. Joel Trop calls it the statistical dimension. And so with the optimal choice of lambda, here is the formula. So the bottom line is what happens is that the ambient dimension is replaced by the statistical dimension when you solve this problem and compare with standard least squares, okay? And so you can, for example, see that if you have any number of measurements below this, things blow up, and that gives you back all the recovery thresholds that Donahoe, Tanner, and others had computed. And so you can actually find this quantity for various examples. For k-sparse signals is what it looks like. For rank R matrices, again, these are approximately true. This is what it looks like for block sparse signals. So you can compute these things and come up with expressions for everything. Okay? And so the curve that I showed you a while back really comes from these formulas. I'm short on time, but I guess you'd believe me. So you can use this method to, as I said, tune the optimal value of lambda, which is an important problem. You certainly can if you know the sparsity, for example, if you know the structure of x naught. So here only the sparsity or the rank shows up. But even if you don't, I'm short on time, there's ways to tune it, given all the machinery we have. And so I will skip this. These are just simulations to show that you can tune things and that things work better. So if I have 2-3 minutes, I want to mention a few generalizations. Okay? So I described the case where sigma goes to 0. When sigma doesn't go to 0, we still have to solve this optimization problem. Again, it's much simpler. It's just a minimization. It's over a vector variable. It's much easier than the min-max that involved Gaussian matrices and all that kind of stuff. It's a little more complicated than what I did, but absolutely doable. And so these are the curves. So for different values of the variance, you have the analytic results versus simulations. This is the cost. We can do other loss functions. So for example, if I want to put an L1 norm here instead of an L2, say if my noise is sparse, this is called the method of least absolute deviations. This is what I would solve. And the only thing that differs is you have to put the dual norm of this when you replace this with a max, and so that's what shows up. The infinity norm does. And so this is what you have to analyze. It's more complicated, but still doable. And when you do it, it perfectly matches simulations. Again, I apologize, I'm going through this fast. So you can do a lot of other things with this. Then there's a question of universality. I assume the entries of A were IID Gaussian. And so the question is, this is necessary. And so simulations suggest the ones that we've done, and we haven't done every distribution, but it seems that as long as you have IID distributed things with the same second order statistics, things work. Okay? We haven't proved this. I've said we're close to proving this. I was hoping to have something to say by now. Maybe if ITA were in June, I could. But so this is an example where we know what the statement is, but the proof is hard. It's the opposite of the Gordon lemma. But just to show you, this is for Bernoulli. IID Bernoulli, again, follows the same analytic curves. We can do Haar matrices. So these are isotropically random unitary matrices. These are not Gaussians. We have a counterpart, I'm short on time, of Gordon's lemma. So we have a capital phi and a little phi. I won't go into it, but the same theorem that applies for the Haar. So these are matrices that have orthonormal rows and that are uniform. And there's a result we have there. These guys behave better than Gaussians, as you would expect, because they don't change norms. So this is what the performance for the Gaussian is. We have a factor here less than 1 that kind of helps. And these are simulations. This is the Gaussian case, the number of measurements versus mean square error. This is the isotropic case. And I'm also showing you empirical results for Gaussians, Bernoullis, discrete, I guess, cosine transforms, Hadamard transforms. And you see things agree quite well. There's something I want to talk about on quadratic Gaussians. So there are situations where you have measurements that are quadratic in G, and you can kind of linearize those too by throwing in a max. This comes up in graphical lasso and phase retrieval. We haven't been able to come up with a comparison lemma for this type of Gaussian process yet. If you do, then I think one can analyze these classes of problems as well. So let me conclude here. Again, I apologize I went fast towards the end because I think the earlier part was more important. So I described a general theory for the analysis of a wide range of structured signal recovery problems for IID Gaussian measurement matrices. As I said, the theory builds on this very simple lemma of Slepian and the generalization of Gordon. But as I showed, it's very powerful. And if you add convexity and strong convexity results, you have these two sets of optimization problems where, even though they don't have the same solutions, you know, if the norm of the solution of one concentrates, the norm of the solution of the other one will as well. And so you learn a lot about the original problem by solving the much simpler one. We can optimally tune the regularizer parameters. We can study all kinds of loss functions in regularizers. The results appear to be universal, though we don't have a proof. We can generalize the theory to isotropically random unitary matrices. And finally, a generalization that I think would be very interesting is if you could do this for quadratic Gaussians. So I will stop here. I don't know if we have time for questions.
So I think we better hold the questions because the sessions are starting. But if you have questions, I encourage you to come up and buttonhole like that.
Thank you.